A loaded train moves through the countryside at walking pace. Nobody gets off. Nothing stops. Yet behind it, a perfectly measured line of crushed stone appears on the track bed, car after car emptying itself in sequence. More than 100 tons of rock released in minutes, placed within inches of a surveyed target. The flow shuts off while the train is still moving. This isn't dumping, it's metering, one of the most precisely controlled operations in modern railroading. Because beneath every freight train hauling 20,000 tons of cargo, a bed of crushed stone holds the rails exactly where they belong. When that stone degrades, the geometry shifts. And restoring it demands getting every gate command, every inch of placement, and every second of timing exactly right. As the heavy consist rolls forward, the transformation of the track bed occurs in plain view. Steel wheels click over jointed rail, and immediately beneath them, a steady stream of sharp gray granite begins to flow. There are no workers on the ground guiding the deposit. No manual levers are being thrown from the platforms, and no cars halt to dump their cargo before moving to the next spot. Instead, the entire train remains in continuous, slow motion, leaving behind a uniform ribbon of stone that matches the profile of the surrounding track. This fluid delivery subverts the typical expectations of heavy engineering. Normally, placing tons of raw aggregate requires stationary dump sites, heavy excavators, and manual grading crews working over several hours. Here, a moving rail vehicle performs a high-volume task that traditionally belongs to a stationary construction site, distributing material with the neatness of a pen, drawing a clean line on paper. The flow starts and stops with absolute precision, never burying the ties or spilling onto the running surface of the rails. The entire train remains self-contained, prompting the fundamental question of how this moving assembly can identify exactly where the track is hungry for material. Manufacturer demonstrations claim these highly specialized systems can release more than 100 tons of crushed granite per minute. Yet in the field, actual throughput rates vary constantly depending on car design, the size of the stone, train speed, and environmental conditions. It is never a simple matter of opening a hatch and letting gravity take over. Unloading rock at this volume usually results in a chaotic, track-burying slide. Here, the system must achieve placement within inches of its target, distributing stone exactly where the track is deficient. Even more challenging is the requirement to halt this heavy cascade instantly. The train does not pause to close its gates. The flow must stop completely, while the massive consist remains in continuous motion. This requirement separates the process from a typical bulk material release. Dumping a pile of aggregate is a basic physical event. Metering a moving stream of sharp, interlocking stones into a precise geometric profile and shutting it off on command is a highly complex mechanical challenge. To accomplish this, a system must simultaneously regulate two conflicting variables: the exact quantity of material discharged and its precise destination on the ground. How a train manages to control this heavy, abrasive flow under constant movement remains the core engineering puzzle. Beneath the massive weight of a moving train, the track bed functions as a highly engineered foundation, starting with the crushed stone packed tightly around and beneath the ties. This material, known as ballast, is heavy, specifically selected aggregate, typically composed of crushed granite, quartzite, or basalt. It is sheared into sharp, irregular pieces rather than smooth, rounded stones. The angular geometry of these individual stones is a deliberate physical requirement. Unlike rounded river stones, which slide past one another under load, these sharp edges bite into each other, locking together to form a rigid, cohesive skeleton. This structural interlocking resists the massive lateral or sideways forces exerted by a train, keeping the ties firmly anchored in their exact positions. In addition to lateral stability, this stone layer serves as a primary load distribution system. When a heavy locomotive passes overhead, The wheels exert immense vertical forces through the rails and ties. The ballast layer takes this concentrated, high-pressure weight and disperses it outward, spreading the load over a vastly wider surface area before it reaches the natural soil or engineered subgrade below. This protects the soft ground underneath from compressing or shifting under thousands of tons of rolling steel. Equally important is the empty space within the rock matrix itself. The natural voids between the interlocking stones create an open path for water. When heavy rain falls, the ballast allows water to drain away immediately, preventing liquid from pooling and softening the earth beneath. Without this rapid drainage, moisture would saturate the soil, turning the foundation to mud and causing the track to sink unevenly. Simultaneously, the ballast acts as a heavy shock absorber. As trains pass, the stone layer flexes slightly, absorbing the intense vibrations and dynamic impacts of rolling steel wheels. This micro-flexibility dampens the intense physical forces that would otherwise damage concrete ties and fatigue the steel rails above, ensuring the entire track structure remains stable under constant use. Constant physical pounding eventually changes the stone itself. As millions of tons of heavy freight pass overhead, the repetitive pressure fractures the sharp, locking edges of the granite. These angular stones gradually grind against one another, breaking down into a fine, powdery dust. This fine material accumulates in the empty spaces between the rocks, slowly clogging the natural drainage paths designed to carry water away. Weather accelerates this physical breakdown. Rain and heavy water runoff can wash away the smaller aggregate from the track shoulders, weakening the lateral support of the entire bed. When rainwater cannot escape the clogged matrix, it pools inside the track foundation. Under the weight of passing wheels, this trapped water is pressurized, forcing mud and fine debris upward through the ballast in a process known as hydraulic pumping. Walking the right-of-way, track inspectors look for these muddy deposits, which signal that the stone layer is failing from within. Maintenance planners analyze these inspection logs and geometry measurements, mapping out where the foundation has begun to lose its uniform support. Once this uniform support degrades, the track's physical geometry begins to shift. Alignment, how straight the track runs along its path, can warp. Gauge, the precise distance between the two steel rails, can widen under lateral loads. Elevation, which is the relative height of the rails on curves, can settle unevenly, creating a wavy profile that causes trains to sway. Under Federal Railroad Administration standards, these geometry defects are directly linked to ballast condition and drainage. If the stone cannot drain, the rails cannot remain stable. National Transportation Safety Board investigations show that when ballast support fails, it creates an unstable foundation. While rarely the sole trigger of an accident, this lack of uniform support frequently serves as a contributing condition in derailment investigations, turning a minor track defect into a serious structural failure long before a heavy train arrives. To prevent structural failures, railroads must place fresh stone, but doing so requires halting the traffic that pays for the infrastructure. The economic penalty for blocking a main line is immediate. Every hour a track is closed carries an estimated freight delay cost of $10,000 to $12,000. When a single segment is taken out of service, a queue of freight trains quickly builds behind the work zone. Locomotives idle, burning fuel. Train crews run up against federally mandated service limits requiring relief crews. Downstream, factories and warehouses experience late arrivals, triggering secondary penalties that ripple through the wider supply chain. This financial pressure converges on two decision-makers with competing priorities. The dispatcher, in a centralized control center, views the network as a fluid system of moving targets, balancing the maintenance window against traffic waiting to use the route. On the ground, the track supervisor manages the physical reality of the work site. The supervisor establishes the limits of the safe work area and decides when the track is stable enough to allow traffic to resume. A traditional stationary dumping operation can consume the entire allocated work window just getting stone onto the ground, leaving no time for the shaping and tamping that must follow. Performing the dump while the train is in motion changes the equation. By dropping stone without stopping, the work train minimizes its track occupancy. The ultimate operational trade-off is simple. The consist must travel slowly enough to place the stone with accuracy, yet fast enough to clear the line before the costs of delayed freight compound. To resolve the tension between rapid transit and exact placement, the railroad relies on a highly specialized machine, the purpose-built open-top ballast hopper. Unlike generic aggregate cars designed merely to transport bulk goods, the vehicle is engineered as a physical solution to a complex moving metering problem. At the quarry, the car is loaded from overhead chutes, receiving raw stone directly into its wide, open top. Once filled, the internal structure of the vehicle takes over. The inside walls are not vertical. Instead, they feature steep, sloped surfaces designed to guide the massive load directly toward the bottom of the vehicle. This geometric taper acts as a continuous funnel, ensuring that every loose stone naturally migrates toward the lower discharge path under the influence of gravity alone. The physical demands placed on this structure are extreme. A standard ballast hopper carries between 100 and 115 tons of dense, angular granite or basalt. During transport, these sharp, interlocking stones constantly shift, creating immense lateral pressure and severe abrasive friction. To withstand this constant grinding, the car is built with a heavily reinforced steel frame, featuring thick structural ribs and wear-resistant interior steel linings. This high-strength construction ensures the car can absorb the repeated high-velocity impacts of loading and the scraping forces of unloading without structural warping. This structural design marks the culmination of a century-long evolution. Early railroad construction relied on flat cars and manual labor, where permanent way crews shoveled tons of stone off the sides of moving trains, a grueling, inaccurate process. The modern hopper replaces this manual labor by acting as a raised reservoir. Rather than tipping the entire car body or dumping the material in a chaotic mass, the hopper stores its heavy loads safely above the rails, utilizing the natural weight of the stone to feed it through precise lower openings. This design keeps the center of gravity stable, transforming a simple hauling container into a highly controlled gravity-fed system. Beneath the sloped steel walls of the hopper car, the gravity-fed stone meets a series of mechanical gates that act more like adjustable valves than simple trapdoors. Instead of dropping the entire payload at once, these gates regulate the volume of the cascading rock by opening to precise, measured widths, restricting or expanding the flow path as needed. Managing this massive weight under constant motion requires significant physical force, which is delivered by specialized onboard actuators. Many modern fleets rely on pneumatic cylinders powered by the train's compressed air lines. Within these actuators, pressurized air forces a heavy piston to slide open the gate. For safety, these systems are designed with a mechanical bias. A robust internal spring is compressed when the gate opens. If the train loses air pressure, the stored energy in the spring instantly forces the piston back, snapping the gate shut to prevent an accidental track-burying spill. In colder climates or on heavier cars, railroads often favor hydraulic cylinders instead. These systems use pressurized fluid to deliver the immense force needed to move heavy steel gates against 100 tons of packed stone, providing reliable physical control regardless of freezing temperatures. Other car designs in active service may utilize electric motors or traditional manual handwheels, meaning no single actuation method is universal. Once the stone passes through the gate, it must be steered to its exact target. Gravity alone is too unpredictable for this process. Beneath each gate, a system of steel chutes and adjustable deflector plates takes control of the falling stream. Chutes carry the falling rock outward away from the car body, preventing it from piling onto the moving wheels or the running surface of the rails. The deflector plates, angled by the crew, change the path of the falling stone. By adjusting these plates, the operator can direct the material to the center of the track, the left rail, the right rail, or the outer shoulder. This mechanical arrangement allows for highly targeted distributions. A crew can dump heavily on the outside shoulder of a sharp curve where lateral force is highest, while leaving the center track completely untouched. Rather than letting gravity dictate the placement, the operator's physical setup guarantees that the material is distributed according to the specific needs of the line. Moving hundreds of tons of stone at a walking pace requires more than just mechanical chutes. It demands a control system that acts as an intelligent supervisor. Instead of relying on manual labor at the side of each car, modern operations rely on remote gate control systems. Operators send commands directly from a locomotive console, a ground controller, or a wireless handheld unit. This remote setup allows a single operator to check the physical status of the gates from a safe distance, receiving real-time feedback on open and closed positions without standing directly next to the active gravity discharge. This electronic management does not replace human judgment. It establishes a system of prepared supervision. Before the train moves onto the active work site, a detailed plan is mapped out, defining the exact start and end points for the ballast release. Onboard computer logic uses this plan to sequence individual gates or coordinate groups of gates across multiple cars simultaneously, maintaining a consistent application rate. Specific areas along the track, such as bridges, highway crossings, and switches, are designated as absolute no-dump zones where the gates must remain locked. Heavy physical and software interlocks act as built-in safeguards, preventing a standard operational movement command from accidentally initiating an uncontrolled release within these restricted zones. Throughout the run, the operator and control team act as the central checkpoint. They monitor live telemetry that logs gate state, cylinder pressure, battery conditions, and individual actuation events, storing this data for safety compliance. This continuous tracking means they verify the system state at every step of the journey, making sure the equipment responds exactly as expected. If a mechanical issue occurs, such as an oversized rock jamming a gate or a sudden drop in hydraulic line pressure, the operator can immediately execute a manual override to halt the flow. This balance between repeatable computer commands and direct human intervention keeps the system safe and stable, preventing a high-volume aggregate drop from becoming a hazardous track blockage. To transform a heavy aggregate drop into a surgical operation, the railroad stops thinking about dumping and begins thinking about metering. An uncontrolled dump simply releases a mass of stone. Metering regulates the discharge to match a precise, pre-calculated need. This transition from basic gravity release to calculated flow begins long before the work train ever reaches the site. First, a survey crew scans the right-of-way, mapping the physical dimensions of the existing track bed. This scan identifies exactly where the stone foundation has settled, washed away, or degraded. The resulting digital map defines a target ballast profile, specifying the precise weight of stone required for every individual foot of track along the route. When the work train arrives, its onboard computer uses this digital map as an active blueprint. High-precision GNSS receivers track the train's location in real time, constantly matching the physical position of each hopper car with the corresponding coordinates of the target profile. As the wheels crawl forward, the system identifies the exact needs of the track structure directly beneath each gate, aligning the physical train with its digital instructions. Instead of relying on a simple open or shut command, the train's automated controller dynamically adjusts the gate position or opening duration. The system monitors live flow feedback from sensors on the doors, checking if the expected volume of stone is actually leaving the car. If the train speed changes or if the stone flow fluctuates, the controller immediately alters the gate opening to compensate, maintaining a steady, calculated output of target tonnage per foot. The physical precision of this system is remarkably tight. For example, Herzog reports that its automated systems can achieve a lateral placement accuracy of approximately plus or minus 2 inches relative to the track center line. While this level of precision represents a manufacturer-specific standard rather than a universal industry average, it demonstrates what is possible when digital data drives heavy machinery. Because satellite signals can easily be blocked, the system does not rely on GPS alone. When the train passes through deep rock cuts, under dense forest canopies, or inside tunnels, an onboard inertial navigation system takes over. This backup system uses gyroscopes and accelerometers to calculate position through dead reckoning, bridging the satellite gap until a clear GNSS signal is reacquired. By linking the pre-work survey, satellite positioning, inertial backup, and real-time gate adjustments into a single continuous loop, the train turns a chaotic dump of raw rock into a highly disciplined, automated distribution process. Precise moving unloading requires a steady crawl, typically between 0.5 and 1 mile per hour, though actual limits vary by equipment and work rules. This walking pace is not just for safety, it is a fundamental element of the flow calculation. At this speed, the physical transition of the stone must align with the distance traveled. If the train accelerates, the stone spreads too thin. If the train slows down, the stone piles too deep. This is where the timing of the gate command becomes critical. A gate command does not execute exactly when the hopper is directly over the target. Because gravity takes time to pull the heavy, interlocking stone through the outlet and down the chute, the system must trigger the gate before the target is reached. Typically, the command initiates 15 to 30 feet ahead of the intended zone. If the train travels too fast, the farther the stone moves through the air while passing through the chute, extending the distance between the release point and the actual landing spot. A command sent at the correct moment will still miss its target if the locomotive exceeds its calculated velocity. Thus, speed control is not a separate locomotive task. It is an active variable in the discharge calculation. The engineer in the cab and the operator supervising the gates must coordinate constantly to maintain this balance. Consider the paired outcomes. If the consist moves too slowly, or if a gate is held open too long, excessive accumulation results, burying the ties and creating an obstruction that can derail subsequent traffic. Conversely, if the train moves too quickly, the thin layer fails to provide the lateral support needed to anchor the track. Opening the gates at the wrong location puts the correct volume of material in the wrong place, creating immediate hazards near switches, bridges, or crossings. By treating speed and gate timing as a single, unified system, the crew ensures that the data chain matches the physical ground beneath the wheels. The freshly deposited stone sits in loose, irregular mounds along the ties, completely raw and uncompacted. Unloading is only the initial stage of restoring the track bed. Before trains can resume travel at normal operating speeds, this loose aggregate must be shaped and compressed to build a rigid support structure. This second phase of the maintenance operation relies on a distinct pair of heavy machines working in a strict, sequential chain: the ballast regulator and the tamping machine. First, the ballast regulator establishes the correct physical profile of the track bed. Utilizing large adjustable steel wings, heavy center plows, and specialized rubber element brooms, the machine sweeps across the rails. The center plows scrape excess stone off the ties and away from the running surface of the rails, preventing dangerous wheel obstructions. At the same time, the side wings pivot outward, gathering the loose granite and pushing it into a uniform, sloped shoulder on either side of the track. This regulation process removes hazardous spill, redistributes excess stone across the track bed, and ensures the shoulders are wide enough to provide lateral stability against curving forces. But a perfectly shaped surface does not equal structural support. Underneath the ties, large voids still remain in the loose stone matrix. To resolve this, the tamping machine follows the regulator. Rather than simply leveling the surface, tamping is a physical process designed to restore firm contact between the ties and the ballast bed. The machine positions its workhead directly over each tie, plunging heavy steel tamping tines deep into the stone on both sides of the wood or concrete timber. These tines vibrate at a specific frequency, typically around 35 Hz, while squeezing together under hydraulic pressure. This intense vibration fluidizes the angular stones for a fraction of a second, allowing them to shift, pack, and lock tightly into the empty spaces directly beneath the tie. When the tines withdraw, the ballast is compacted into a dense interlocking foundation that supports the heavy vertical loads of passing traffic. To accelerate this process, on high-density corridors, some continuous action machines combine or tightly coordinate these functions. These advanced assemblies manage ballast handling, shaping, and tamping in a single continuous pass, utilizing a split-frame design where the tamping workhead indexes from tie to tie while the main vehicle continues to roll forward without stopping. Once the physical compaction is complete, the final phase of the maintenance sequence is verification. A post-work geometry check utilizes specialized inspection cars equipped with lasers, optical sensors, and inertial measuring units to verify track alignment, gauge, cross-level elevation, and overall support conditions. This rigorous inspection ensures the finished work meets strict safety standards before the line is reopened. From the initial laser survey and GPS-guided unloading to the physical work of regulation, tamping, and final inspection, every step of this coordinated maintenance sequence serves a single structural purpose. This old railroad job, performed at a slow, walking pace, is the precise engineering process that keeps the track beneath a 20,000-ton freight train exactly where it belongs. Railroads do not rely on a single universal car design to move and deposit ballast. While the automated hopper serves as the standard tool for fine in-track maintenance, other operations require a fundamentally different approach to handling bulk material. On new construction projects or lines requiring massive shoulder repairs, maintenance planners select side dump cars. These heavy steel vehicles are built with a tilting body that pivots on its frame, or side gates that swing open, to discharge the entire payload laterally in a matter of seconds. This rapid, high-volume release places a large amount of stone exactly where a new track bed or a collapsed slope needs immediate structural support. Yet this bulk lateral dump lacks the metering control required for routine track bed maintenance. Tipping 100 tons of rock in a single motion next to the rails would bury the track and obstruct traffic on an active line. Deploying the wrong equipment on an active corridor can quickly create a massive cleanup problem, rather than solving a minor structural defect. This operational variation often leads to confusion regarding terminology, particularly with the term AIR dump. In railroad fleet maintenance, the term air dump often describes standard hopper cars equipped with pneumatic gate actuators, rather than a completely separate body design. When these air-operated outlets are paired with sloped hopper walls, they still allow for precise, proportional metering. The compressed air lines simply provide the mechanical force needed to open and close the gates quickly, maintaining the steady flow required to deposit a calculated weight of stone per foot of track. Ultimately, the choice of equipment depends entirely on the physical requirements of the job. When a project demands rapid construction or a heavy buildup of a washed-out shoulder, planners deploy side dump cars for immediate bulk lateral placement. For standard maintenance of waste cycles, where the goal is to restore a measured profile without wasting material or blocking the line, the controlled bottom placement hopper remains the essential tool. Matching the specific machine to the structural challenge ensures the work train restores the foundation with minimal waste, keeping the track stable under the unyielding weight of daily traffic. As the ballast train crawls forward, a sudden shift in the telemetry breaks the rhythm of the run. Inside the cab, a sensor flags an abnormal hydraulic pressure spike or a mismatch in gate travel before any physical trouble is visible on the ground. An oversized piece of granite, sheared larger than the design limit, has lodged against the steel lip of a gate. The obstruction halts the door's progress, leaving the outlet partially open. In colder climates, a different physical barrier takes shape. Moisture trapped within the hopper can freeze the aggregate solid against the sloped interior walls, locking the heavy load into a rigid block that completely interrupts the expected flow. Whether the cause is a frozen load, a physical jam, or a clogged discharge chute, the resulting blockage creates pressure and flow conditions that lie completely outside the controller's software assumptions. When an outlet fails to close on command, the consequences are immediate and severe. The system can dump tons of uncontrolled rock onto a restricted track feature like a switch, crossing, or bridge, or pile it dangerously high on a shoulder where it does not belong. Conversely, uneven distribution from a sluggish gate can overload one section of the track bed while leaving the adjacent sleepers entirely starved of the structural support they need to resist the lateral forces of rolling traffic. Resolving this anomaly requires a highly coordinated diagnostic sequence rather than individual heroics. The ballast operator on the ground instantly reports the gate error over the radio. In the locomotive, the engineer manages the train's movement, reducing speed or bringing the heavy consist to a controlled stop within a pre-planned safe work zone. The track supervisor oversees the entire response, validating safety protocols and track limits before authorizing the crew to step out. Together, these crew members work through a methodical checklist to determine whether the abnormality is mechanical, material-related, positional, or operational. If the blockage is a physically wedged rock, the crew must safely depressurize the pneumatic or hydraulic actuators to clear the obstruction manually. If the system suffered an electronic drift, they recalibrate the gate sensors before resuming the run. However, even a brief operational failure leaves a physical footprint on the right-of-way. A bad release creates a new track geometry problem, rather than solving an old one. Overdumped stone can bury ties or foul the rails, while underdumped areas fail to anchor the track. Correcting these errors forces the railroad to perform additional maintenance cycles. The ballast regulator and tamping machine must make extra passes to redistribute and pack the misplaced stone, followed by fresh geometry inspections. In the worst cases, a failed automated dump can require a full-stop track closure to manually clear the line, turning a rapid maintenance run into the very delay it was meant to prevent. The necessity of supporting heavy rails with crushed stone is as old as the railroad industry itself. In the mid-19th century, track gangs used shovels and wheelbarrows to distribute ballast, relying entirely on physical stamina and visual estimation to establish a level bed. Today, even with high-precision satellite tracking and automated gate actuators, the fundamental engineering challenge remains identical. The transformation of this task does not alter the basic physics of track support. It represents a major evolution in safety, consistency, and physical exposure. While digital mapping and pneumatic valves have replaced the intense physical strain of manual labor, they have not eliminated human judgment. Instead, that operational judgment has been transferred upstream. It now exists within pre-work laser surveys, calculated gate response algorithms, and the precise velocity settings managed in the locomotive cab. Even as onboard computers regulate the flow, the modern consist still advances at a slow, deliberate walking pace. This crawl links the manual track-laying crews of the 19th century with the data-driven systems of the 21st, maintaining a physical rhythm that has defined track maintenance for generations. Every modern role belongs to a single, coordinated chain of responsibility. The survey engineers who map the track, the remote operators who monitor the gates, the regulator and tamper crews who shape the stone, and the inspectors who verify the final profile all work toward a single objective. Their collective effort protects the unseen physical geometry of the right-of-way. While a ballast train itself weighs only a fraction of a standard payload, the quiet stability of the compacted rock bed it leaves behind is what supports the massive weight of a 20,000-ton freight consist. This visible, slow-motion release of stone serves as the ultimate shield for the invisible lines of force running through the rails, keeping the heaviest trains safely aligned exactly where they belong. Today, our modern supply chains still depend on these steel arteries. As freight loads grow heavier and schedules tighter, the margin for track failure shrinks to zero. This continuous flow of rock isn't just maintenance, it is the invisible shield protecting global commerce. The next time you see a train pass, remember the silent, calibrated foundation beneath it. What other hidden engineering marvels keep our world moving? Share your thoughts in the comments below.